Hello? Today, I want to talk to you about something that was one of the most significant experiences of my life. My time working on the Manhattan Project during World War II. This was the secret project to build the atomic bomb, and I was there at Los Alamos, in the middle of the desert in New Mexico, working with some of the greatest physicists in the world on something that would change history forever. Now, before I get into the details, let me tell you how I got involved. I was a young guy, just finishing my PhD at Princeton in 1942. I was working on my thesis, doing theoretical physics, and I got approached to work on this secret project. At first, they couldn't tell me what it was about. They just said it was important war work. But eventually, Robert Wilson, who was recruiting people, told me they were trying to build a bomb using nuclear fission. If you enjoyed exploring these ideas with me today, I'd appreciate it if you'd subscribe to this channel. There's so much more fascinating physics to talk about, from quantum mechanics to the nature of reality itself. Every subscription helps us continue making these educational videos and sharing the wonder of understanding how the universe works. Hit that subscribe button, and let's keep exploring the mysteries of science together. I knew about fission. Everyone in physics knew about it. It had been discovered just a few years earlier, in 1938, by Otto Hahn and Fritz Strassmann in Germany, though it was Lise Meitner and Otto Frisch who really understood what was happening. They found that when you bombard uranium with neutrons, the uranium nucleus can split apart into smaller pieces, releasing enormous amounts of energy. And here's the key part. When the nucleus splits, it also releases more neutrons. These neutrons can then split other uranium nuclei, which release more neutrons, and you get a chain reaction. The energy released per atom is enormous. It comes from Einstein's famous equation, E equals mc squared. When the uranium nucleus splits, the total mass of the pieces is slightly less than the mass you started with. That tiny bit of missing mass has been converted to energy. And because c, the speed of light, is such a large number and you're squaring it, even a tiny bit of mass converts to an enormous amount of energy. Now, here's what makes a bomb possible. If you have a piece of uranium that's big enough, a critical mass, then when one nucleus splits and releases neutrons, those neutrons are likely to hit other nuclei before escaping from the material. This causes more splits, more neutrons, more splits, and the whole thing cascades in a fraction of a second. All that energy gets released almost instantaneously. That's an atomic bomb. The question was, could we actually build one? Was it practical? And more urgently, were the Germans working on it? We knew they had excellent physicists. We knew they understood fission. If Hitler got an atomic bomb before we did, it would be a catastrophe. That's why so many of us agreed to work on the project, even though we were scientists who preferred to work on understanding nature, not building weapons. So I joined up. At first, I was at Princeton, doing calculations. But in 1943, the project moved to Los Alamos, a remote location in the mountains of New Mexico. The idea was to bring all the scientists together in one place where they could work in secret and collaborate directly. The site was chosen partly because it was isolated, easy to secure, and partly because Robert Oppenheimer, who was leading the scientific effort, loved that area. He'd spent time there as a young man. When I arrived at Los Alamos, it was barely built. There were muddy roads, construction everywhere, barbed wire fences. Everyone lived in simple quarters, and we all worked in hastily constructed laboratories. But there was an incredible energy to the place. You had some of the greatest minds in physics all working together. Oppenheimer, Beth, Teller, Fermi, Bohr when he visited, and many others. Young guys like me were working alongside these legends. My job was theoretical calculations. I was in the division led by Hans Bethe, who was just brilliant. We had to figure out all sorts of things. How much uranium or plutonium would you need for a critical mass? How fast would the chain reaction proceed? How much energy would be released? How would the bomb material behave under the extreme conditions of compression and heat? These weren't easy questions. We were dealing with physics that had never been tested before, conditions that had never existed except perhaps in the cores of stars. One of the challenges was that we needed to do enormous amounts of calculation, and we didn't have computers in the modern sense. We had people, mostly women actually, who operated mechanical calculators. They were called computers because that was their job, to compute. I got involved in organizing this human computing effort, figuring out how to break down the calculations into steps that could be done in parallel, how to check for errors, how to speed things up. It was like programming, but with people instead of machines. I also got involved with the IBM punch card machines they brought in. These were the closest thing we had to automated computers. You could program them, in a sense, by wiring up plug boards. I figured out how to make them do some of our calculations, and I found it fascinating. This was my first real experience with computation, and it influenced my later work in physics and computer science. But let me tell you about the science itself, because that's really what drove everything. The basic idea of the bomb was straightforward. Get enough fissile material together fast enough, and you get a chain reaction. But the details were devilishly complicated. First, you need the right kind of uranium. Natural uranium is mostly uranium-238, which doesn't work well for a bomb. You need uranium-235, which makes up less than 1% of natural uranium. Separating U-235 from U-238 is incredibly difficult because they're chemically identical. The only difference is a tiny difference in mass. The Manhattan Project built enormous facilities to do this separation using various methods: gaseous diffusion, electromagnetic separation, and others. It took a massive industrial effort. The other option was plutonium. Plutonium doesn't exist in nature, but you can create it in a nuclear reactor. When U-238 absorbs a neutron, it eventually decays into plutonium-239, which is fissile. So part of the Manhattan Project was building reactors to produce plutonium. Fermi had built the first nuclear reactor in Chicago in 1942, proving it could be done. Then they built huge reactors at Hanford in Washington state to produce plutonium for the bomb. Now, once you have your fissile material, you need to assemble it into a bomb. But there's a problem. If you just put two pieces of uranium together to make a critical mass, they start to heat up from the beginning of the chain reaction, and they blow themselves apart before most of the nuclei have split. You get what we called a fissile, a small explosion that wastes most of the material. The solution is to assemble the critical mass as fast as possible. For the uranium bomb, we used what's called a gun design. You take two pieces of uranium, each smaller than critical mass, and you shoot one into the other using conventional explosives. They come together so fast that the chain reaction completes before the material has time to blow apart. This design was relatively straightforward, and we were confident it would work. But plutonium was trickier. Plutonium has an annoying property. It tends to have impurities that cause premature fission. If you tried to use a gun design with plutonium, the material would start to fizzle before the pieces fully came together. So we needed a different approach. The solution was implosion. Instead of shooting two pieces together, you take a sphere of plutonium that's less than critical mass, and you surround it with conventional explosives. When you detonate the explosives, they compress the plutonium, squeezing it to a higher density. At higher density, it becomes supercritical, and the chain reaction takes off. The compression has to be perfectly symmetric, or the plutonium will squirt out the sides. This required incredibly precise engineering. I worked on some of the calculations for the implosion design. We had to figure out how shock waves would propagate through materials, how the plutonium would compress, what would happen to the neutrons. It was challenging physics, and we learned an enormous amount about the behavior of matter under extreme conditions. There was also the question of the initiator, the urchin as we called it. You need to start the chain reaction at exactly the right moment, when the material is fully compressed or fully assembled. We used a device that mixed beryllium and polonium. When compressed, they produce a burst of neutrons to initiate the chain reaction at the optimal moment. All of this had to be figured out, tested, and built in just a few years. It was an incredible engineering and scientific effort, and it all came together in July 1945 with the Trinity test in the New Mexico desert. I remember that test vividly. We were all nervous. We'd done the calculations, but you never really know until you try it. Would it work? Would it be a dud? Some people even worried, half seriously, that the bomb might ignite the atmosphere and destroy the world. We'd calculated that this was impossible, but there was still that little voice of doubt. We were stationed at various observation points miles away from Ground Zero. It was early morning, still dark. Then came the countdown. And then, suddenly, there was this enormous flash of light, brighter than anything I'd ever seen. The whole landscape lit up like daylight. Then came the blast wave and the mushroom cloud rising up into the sky. It was awe-inspiring and terrifying at the same time. We'd done it. We'd released nuclear energy on a macroscopic scale. The test yield was about 22 kilotons of TNT equivalent. That's 22,000 tons of TNT going off in an instant. From the physics calculations we'd done on paper, from the experiments we'd run, we'd created this incredible, terrible thing. The feeling was complicated. On one hand, there was pride and excitement. We'd solved an incredibly difficult scientific and engineering problem. We'd done something that had never been done before. But on the other hand, there was a sense of dread. We knew what this weapon was going to be used for. We knew it was going to kill people, potentially many people. After the Trinity test, things moved quickly. A uranium bomb called Little Boy was dropped on Hiroshima on August 6, 1945. 3 days later, a plutonium bomb called Fat Man was dropped on Nagasaki. The destruction was beyond anything the world had seen before. Hiroshima was essentially destroyed. Estimates are that around 140,000 people died in Hiroshima by the end of 1945, and around 70,000 in Nagasaki. Many more died later from radiation sickness and cancer. Japan surrendered on August 15, 1945. The war was over, and we, the scientists who had built the bomb, had to grapple with what we'd done. I remember after the war there were celebrations at Los Alamos. People were happy the war was over, relieved that we'd succeeded. But I felt differently. I would be walking around, and I'd look at the buildings in the city, and I'd think, how vulnerable they are. It would be so easy to destroy all this. I couldn't stop thinking about what atomic bombs meant for the future of humanity. Many of us felt this way. We'd built the bomb because we were afraid Germany would build it first. But Germany had never gotten close. Their nuclear program had failed for various reasons: lack of resources, scientific mistakes, Hitler's distrust of theoretical physics as Jewish physics. By the time we tested the Trinity device, Germany had already surrendered. The bomb was used on Japan, not Germany. There's been endless debate about whether it was necessary to drop the bombs on Japan. Some argue that it ended the war quickly and saved lives that would have been lost in an invasion of Japan. Others argue that Japan was already on the verge of surrender and that the bombs were unnecessary. I don't know. I wasn't making those decisions. I was just doing the physics. But I do know that after the war, many of us felt a responsibility to speak out about the dangers of nuclear weapons. Oppenheimer became an advocate for international control of atomic energy. He opposed the development of the hydrogen bomb, which would be even more powerful. This got him in trouble during the McCarthy era, and his security clearance was revoked in a hearing that was really a political attack. Other scientists, like Leo Szilard, who had been one of the first to understand the possibility of a chain reaction, became activists for peace and nuclear disarmament. Einstein, whose famous equation E equals mc squared had helped us understand where the energy came from, later said that if he'd known Germany wouldn't succeed in building the bomb, he never would have supported the project. As for me, I went back to physics. I went to Cornell, then to Caltech, and I worked on fundamental problems in quantum mechanics and particle physics. I tried not to think too much about the bomb, but it was always there in the background. The genie was out of the bottle. Nuclear weapons existed, and they weren't going away. The Manhattan Project changed the world in profound ways. It ushered in the atomic age. It led to the Cold War arms race between the United States and the Soviet Union, with both sides building enormous arsenals of nuclear weapons. It led to the doctrine of mutually assured destruction, where both sides had enough weapons to destroy each other completely, which paradoxically might have prevented World War III. Nuclear weapons also led to a greater awareness of the responsibilities of scientists. Before the war, most scientists saw themselves as seekers of knowledge, working on understanding nature, pure research, motivated by curiosity. But the Manhattan Project showed that scientific knowledge could have direct and immediate practical consequences, for better or worse. Scientists could no longer claim to be working in isolation from society. There were positive outcomes too. Nuclear energy can be used for electricity generation. Nuclear medicine uses radioactive isotopes for diagnosis and treatment. Our understanding of nuclear physics expanded enormously. Many of the techniques we developed, from computational methods to instrumentation, found applications in peacetime science. But the shadow of nuclear weapons remains. There are still thousands of nuclear warheads in the world, many on high alert, ready to be launched within minutes. The danger of nuclear war, whether by accident, miscalculation, or deliberate choice, is still with us. And now, more countries have nuclear weapons than during the Cold War. The danger has, in some ways, increased. Looking back, would I do it again? I don't know. At the time, it seemed necessary. We thought we were in a race with Germany. We thought Hitler might get the bomb. But knowing what I know now, knowing how it was used, knowing how it changed the world, I'm not sure. What I learned from the Manhattan Project goes beyond the physics and the engineering. I learned about how science can be applied to practical problems on an enormous scale. I learned about collaboration, about how bringing together talented people and giving them a clear goal can lead to remarkable achievements. I learned about the power of theoretical calculations combined with experiments, and I learned about the responsibilities that come with knowledge. The Manhattan Project demonstrated both the best and the worst of what humans can do. The best, brilliant minds working together, solving incredibly difficult problems, pushing the boundaries of what's possible. The worst, using that brilliance to create weapons of mass destruction, to kill on an unimaginable scale. I think the key lesson is that scientific knowledge is morally neutral. E equals mc squared is just a fact about nature. It doesn't care whether you use it to build a bomb or to understand how the sun produces energy. The moral questions come in how we choose to use our knowledge. And those are questions that can't be answered by physics or mathematics. They're human questions, requiring human judgment. As scientists, we have a responsibility to think about the consequences of our work, not just the immediate technical problems, but the broader implications. What will this be used for? Who will benefit? Who might be harmed? These are difficult questions, and there are no easy answers. But we can't simply ignore them and say, I'm just doing the science. At the same time, I don't think scientists should stop pursuing knowledge. Understanding how nature works is valuable in itself. It's part of what makes us human. And you never know what seemingly abstract piece of knowledge might turn out to be important. Quantum mechanics seemed like pure theory, and now it's the basis for transistors and computers and lasers. The question is how to balance the pursuit of knowledge with responsibility for how that knowledge is used. I don't have a perfect answer. I don't think anyone does. But I think it's important to keep asking the question. After the war, I tried to get back to normal life, back to just doing physics. But the experience of Los Alamos stayed with me. It shaped how I thought about science and society. It made me more aware of the real-world implications of theoretical work, and it gave me a healthy skepticism about authority and government secrecy. One thing I found frustrating at Los Alamos was the security culture. Everything was compartmentalized. You weren't supposed to talk to people in other divisions about what you were working on. You weren't supposed to know more than you needed to know for your specific task. But this made the work less efficient. Science works best when people can share ideas, when you can walk down the hall and talk to someone about a problem. I used to break the security rules regularly. I'd talk to people in other divisions about their work. I'd look at classified documents I wasn't supposed to see. I even figured out how to pick the locks on the safes where classified documents were kept, partly as a challenge, and partly because I wanted to show how inadequate the security was. I never stole anything or shared secrets with unauthorized people, but I did it to prove a point that too much secrecy can be counterproductive. This experience gave me a lasting distrust of excessive classification and compartmentalization of knowledge. Information wants to be free, or at least, science works better when information can flow freely among people working on a problem. Another thing I learned was about the culture of physics and how physicists work together. At Los Alamos, we had this amazing collection of people, and there was a real sense of camaraderie. We worked hard, but we also played. We had parties, we went hiking in the mountains, we had informal discussions about physics problems. Oppenheimer created an environment where ideas could flow and where young people like me could contribute alongside the established leaders in the field. This taught me that doing good science isn't just about individual genius. It's about creating an environment where people can collaborate, where they can challenge each other's ideas, where they can fail and try again. Some of the best insights came from informal discussions, from someone asking a naive question that made us all rethink our assumptions. The Manhattan Project was also a demonstration of what's now called big science, large-scale scientific projects involving many people, massive funding, and close connections to government and military. This was different from the traditional image of the lone scientist in their laboratory. After the war, this model continued with projects like particle accelerators and space programs. There are advantages to big science. You can tackle problems that are too large for any individual. You can build equipment that's too expensive for a university to afford. But there are also dangers. Science can become bureaucratic. It can become driven by politics and funding rather than by curiosity and the pursuit of understanding. The connection to military funding can skew research priorities. I've always tried to maintain a balance. I've worked on big projects, like the theory of quantum electrodynamics and particle physics. But I've also valued small-scale, curiosity-driven research. Some of my best work came from just playing around with ideas, following my curiosity wherever it led, without worrying about whether it would be useful or fundable. Looking back now, decades later, the Manhattan Project seems like a pivotal moment in history. It marked the beginning of the nuclear age. It demonstrated the terrible power that comes from understanding the atomic nucleus. It showed that theoretical physics, which had seemed so abstract and removed from everyday life, could have immediate and profound practical consequences. For me personally, it was an intense, formative experience. I was young, in my mid-20s, and I was working with the best physicists in the world on the most important scientific project of the war. It was exciting and terrifying. It taught me an enormous amount about physics, about problem solving, about collaboration, but it also left me with a sense of unease about the responsibility that comes with scientific knowledge. The question of whether the bombs should have been used, whether the project was morally justified, these are questions I've thought about many times. I don't have definitive answers. I can see arguments on both sides. What I do know is that the development of nuclear weapons changed the world permanently. We can't uninvent them. We have to live in a world where these terrible weapons exist. The best we can do is to work toward a world where they're never used again. That means arms control. It means diplomacy. It means education about the dangers of nuclear war. It means scientists speaking out about the consequences of these weapons. It means all of us, scientists and non-scientists alike, taking responsibility for the world we're creating. I sometimes wonder what those young physicists I knew at Los Alamos would think if they could see the world now. Some of them are gone. Oppenheimer died in 1967, troubled and conflicted about his role in creating the bomb. Beth lived to a very old age and became an advocate for nuclear disarmament. Teller went the opposite direction, pushing for more and bigger weapons. We all processed the experience differently. As for me, I tried to move on, to contribute to physics in other ways, to teach, to explain science to the public. But Los Alamos is always there, a part of my history. It's a reminder that science is not just equations on a blackboard. It's part of the real world, with real consequences. And as scientists, we have to think about those consequences, even as we pursue the beautiful goal of understanding how nature works. Thank you.